Good afternoon and welcome to this Chemistry World webinar. I'm Ben Valsler, Chemistry World's digital editor. Now today we're looking at the age of digital chemistry. We'll learn how data can solve existing bottlenecks in synthetic chemistry and why data analysis demands a multidisciplinary approach. Now, it's kind of hard to argue that now our lives are dictated by data, and this has transformed the scientific landscape and agenda across academia and industry. Now, this in turn is going to require a new generation of R&D scientists and engineers who know how to collect, analyze, and utilize a large quantity of chemometrics data, as well as understand the complexity. So over the course of the next hour, we will discuss some of the ways that data can be used to solve the existing bottlenecks in synthetic chemistry, and also some of the future challenges for the discipline. We'll look at how a multidisciplinary approach teaching industry relevant skills like design of experiments is important to Imperial College's industrial partners. Now we have two guests with us today. I'll introduce them in a few minutes, but first what I'd like to do is just try and find out a bit more about you as an audience. And so what we're going to do is we're going to run a quick poll where we're asking you what sort of work you do, and that will allow us to just to get to know you a bit. So there are still people arriving, so if you're arriving now, this poll is just to find out a little bit more about you. So what is your background? Are you teaching at university? Are you a researcher? Do you work in analytics in industry? Do you work in the chemical industry, or do you have a chemical background, or do you work in biotech or pharma? And while people are completing the poll, I will also tell you how you can use GoToWebinar, which is the platform that we've chosen to use in order to ask questions and interact with our speakers today. Now, the most important thing, or the easiest way for you to interact, is probably down at the bottom of the GoToWebinar panel. There will be a box that just allows you to ask questions to the speakers. So type your question in there and we will be able to get through it. We will have a Q&A session at the end of the presentation. So today we have a presentation and we have a software demo, after which we'll go to Q&A. But you should get your question in as soon as it occurs to you. Don't wait until the end in case we do run out of time. We often get a lot of questions in during the course of a webinar. So for the best chance of your question being answered, get it in as early as you can. We'll have a couple more polls throughout the webinar as well, so they're a very good opportunity. If you haven't quite formed the right words for your question, it's a good chance while the poll is taking place that you can type your question in at that point. I can see already we've had a couple of questions in, so clearly there's a lot that people want to know about this topic, and it would be good to get your questions in as soon as possible. You also will have noticed my webcam at the beginning there, as well as the screen that we were sharing. If you're on a slow connection or if you have any issues like that, there's a button above where my face has appeared that allows you to switch off webcams or just choose to show the one. So when we're presenting the Q&A at the end, we'll have all the three of us on screen. If you're on a slow connection, turn the webcams off. That will make sure you still see what's happening on screen, you still hear what's being said, but it won't eat too much into your bandwidth. Right, I think that's probably enough time now for this initial poll. Let's get those results on screen now, and we can see that, right, so half of the audience are researchers, a third roughly teaching at university and in the chemical industry. Clearly you could tick more than one box, which is why these don't add up to 100, in case you were wondering. It's good to see that you already got an eye for doing a bit of data correction and analytics there. 8% in biotech and pharma, 8% in analytics in industry. So it's a reasonable spread throughout the chemical industry and academia, with a slight lean towards teaching and research. So thank you for letting us know who you are. It really helps us to know what we put into our webinars. It helps us to choose future webinars and to find the right partners for our webinars. And in particular, I should mention our partner for this webinar and a series of webinars throughout 2021 is JUMP. Now, they're an excellent partner that we work with a great deal. JUMP themselves make software, statistical discovery software that helps you to design your experiments properly and to analyze them properly, and then to share that information, which can be extremely useful for convincing people that they need to change path, or convincing people you're on the right path, or just tweaking experiments or tweaking industrial processes in order to make sure that you're doing exactly the right thing and being as efficient as possible. Their software is easy to use and very innovative, so we're delighted to have them with us as a regular partner for our webinars. So just to reiterate, over the course of the next hour, we'll be looking at the current challenges of synthetic chemistry, such as the dialer molecule grand challenge. We'll be looking at types of data that are available to you in chemistry, so that's data enabling tools that are currently available. We'll look at common misconceptions of high throughput chemistry. We'll look at future challenges in terms of hardware, software, and expertise. And we'll be looking at initiatives that are taking place at Imperial College London, such as DigiFab, so the DigiFab Institute, RAW, and the REACT CDT. And giving us most of that information about Imperial College London is our first guest today, Mimi Hii. Now, Mimi is Professor of Catalysis at the Department of Chemistry at Imperial College London. She's the founder and director of the Centre for Rapid Online Analysis of Reactions, that's RAW, which is an excellent acronym. She's also the director of the EPSRC Centre for Doctoral Training in Next Generation Synthesis and Reaction Technology, that's REACT, another excellent acronym. And she's currently an associate editor for the ACS journal Sustainable Chemistry and Engineering. So Mimi's going to take us through the initial presentation, after which we will hand over to Volker Kraft, who is a JUMP academic ambassador for Europe, senior academic ambassador, in fact. Background in electrical engineering, he uses statistical methods to study psychoacoustics and speech communication. He's employed those in industry. He now works for JUMP, helping people to use their software to make the most of their research. But Mimi has joined us on screen. Thank you for joining us, Mimi. It's lovely to have you with us. I will hand across to you now to do your presentation, and we'll come back for Volker and then some Q&A later on. So once again, keep those questions coming in, but for now, sit back and enjoy Mimi's presentation. Thanks again for joining us.
Thank you very much, Ben. I hope everybody can hear me okay. So let me start off by saying, thank you, RSC, Ben, and also Volker for inviting me to present something on the webinar today on this big topic, the age of digital chemistry. So I think, so by the poll, that's quite interesting. So I just assume researcher plus academic means most of you are probably here to find out a little bit more about what it can do for you and maybe, where you could get started. So, so I'll just always start to kind of start off with a bit of a disclaimer in the background. So where I'm coming from. So for those of you who doesn't know me already, I'm speaking here primarily, my background is in synthetic chemistry, organic, inorganic. So I'm coming towards the topic as an experimentalist. So I have to first of all say I'm not a mathematician, I'm not a programmer, I don't, I dabble a little bit in DFT calculations, but fundamentally I'm not classifying myself as a computational chemist. So my interest is very much on data, how to generate data, how to interpret data, and then make them work for me. So I see this whole idea of digital chemistry. Is this, again, just like with most things in technology, it's just a tool. How could it get me to do my work better, faster, and smarter? So while I have a great deal of respect for people who develop these digital tools to make our life easier, I'm not an expert by any stretch of imagination. So I'll apologize in advance if there's those of you in the audience who, work in this area, quite a lot of expertise in this area, and I'll probably use some wrong terminology during my talk that would probably make you wince a little bit. So I'll apologize for it. But in my defense, the way we teach, certainly organic chemistry, the way, I tell my students is, knowing the name of a reaction is far less important than knowing what the reaction can do itself. So in that spirit, let us get started. I'd like to share with you is also our experience starting from quite a traditional synthetic chemistry background and actually really come into this area, I would say no more than 4 or 5 years ago, actually start doing some of these things that I wanted to do and what our experience has been like and what I could see that for future, for certainly in the area of synthetic chemistry, in the directions that it will go in this very fascinating area of digital chemistry. Okay, so get started with my slide. Okay, so let's just start with, now that it's given that this is an RSC event, let's just start with looking at some of the articles. I mean, clearly this is a very hot topic. It's been covered over the years. You will see there's some articles from industry, from academia, and actually from the Royal Society itself, all kind of delving in this issue from many perspectives. So undoubtedly, this is a very important issue. Myself, I've been involved. Some of you may have heard about the EPSRC Dial Molecule Grand Challenge, which I was involved in the last phase 3, as a co-I. So, it is about time that we decided about 5 years ago to actually really, rather than just talk about it, to actually do something about it. And during today's talk, I'm going to share some of these initiatives with you, and our experience and our lessons that we learned in this journey. One thing that's very exciting for me personally is this whole multidisciplinary approach to synthetic chemistry, working with obviously biologists on one hand, physical chemists on the other hand, and Volker, you would have heard for the introduction, he's not even a chemist, he's an electrical engineer, but we all have this common goal of using this tool to kind of develop our workflow and really bringing I think it could be fundamentally very transformative. It's not just a thing that you buy in the lab. It actually transforms everything we do, how we teach our students, how we do our research, and actually going forward, how we plan future of chemistry as a discipline itself. So I think this is a very exciting time to be a chemist for sure. Okay, so before we start, so all of you no doubt would have heard about, seeing almost on the news every day about fantastic things, what AI can do. So for sure, the last few years, very often people come up to me and make one of these two statements, and I would just like to kind of address some of these misconceptions. So we heard a lot about robotic chemistry, and you've seen the headlines, you've seen the news, you've seen the pictures of robots such as that who can go around the lab doing experiments, who can churn out reactions, thousands of reactions, a day. Well, we're just going to examine that a little bit, that statement a little bit today, I find. And the second thing is kind of a little bit more of an existential crisis, say, well, if robots can do this, wouldn't it just replace synthetic chemists? Well, this is a very interesting question. So again, we're going to examine that a little bit. So the answer is both yes and a no, because it kind of challenges us of what we do actually as synthetic chemists, day to day, what do we do? And if you answer in a certain way, then yeah, the answer may be yes, your role could be replaced by a synthetic chemist, by a robot, sorry. And but it really challenge you to start thinking about what you may want to do your work perhaps a little bit differently in the future. Didn't really say that very well, but okay, so first of all, will robots take our jobs? I think for sure with the pandemic, there's a great realization that maybe all this robotic stuff may seem to be a bit fancy and a bit of a luxury almost. It has now become almost more of a reality, with this social distancing and stuff. So you would have seen some headlines of certain jobs being overtaken by robots, which you can disinfect easily and not transmit viruses and stuff like that. So it certainly has come to the top of the agenda for a lot of funding agencies, and EPSRC, for example, as almost every other day, have some sort of call on digital chemistry and digitization. So let's just look at the cold hard facts. What can a machine do? I mean, I'm sure we are all surrounded by machines and robots, right? And we all have Alexas or Googles, what have you, which is supposed to be these kind of artificial intelligent and enabled devices. But fundamentally, at least at the moment, or the current state of play is a machine certainly can only do what you tell it to do. And the second thing is, more importantly for synthetic chemists, there's no magic, so as I said before, a robot may be able to do something, very well repetitive. It cannot do what you cannot do as a synthetic chemist. So basically, it is still very much what they do is still need to be informed by a synthetic chemist. You could never really replace, our creativity and our thoughts and the way that the way we solve problems, for sure. There's still some way to go before machines can do that. However, what a machine can do, it can certainly change the way we do things. So here in this table, I kind of adapted it from this kind of consultancy company, which published an article online about, these things, about 20 jobs that will be replaced by a machine in the next 20 years, and 20 jobs that will not be replaced by a machine, by a machine or AI. So interestingly, just going down, you're looking for chemist relevant things, you will see that jobs that robot will replace in future are manufacturing and pharmaceutical work. And if you look at the narrative a little bit, they say about, it's the kind of boring, repetitive jobs that you do. So one very simple example I can think of is, for example, column chromatography. I mean, in a lot of labs, that's already been replaced by an autocolumn, for example. But if you just think back, 10 to 20 years ago, when it's not so widespread, we were still doing a lot of these things by hand. And I don't think any of us will complain if, some of these repetitive jobs could be, taken by a machine. And what that would then free us to do is to kind of be creative, be good at what we're good at as human beings, be creative, be imaginative, be adventurous, all that kind of good stuff. And that kind of brings me to the kind of second column as scientists, because I like to think as scientists that this is what our value is. We know what we want to achieve. We set the problems. We want to solve a problem, good at solving a problem, be imaginative and creative. This is what a scientist is. A scientist shouldn't be somebody who just repeats something over and over again in the laboratory. Or at least that's not what I like to do anyway. Okay, so robot and chemistry, let's kind of look at it a little bit more. So this is just an example, deliberate example of a molecule that is, I hope you can all appreciate, very highly complex. So to be fair, if you look at, examine a lot of these claims a little bit, what are the problems that chemists faces day to day, and how much can a robot or machine help us to solve some of the problems we have? So let's just say we want to make this molecule. Okay, discounting some very basic reactions, adding acid to base to form an adduct or salt, for example. Most chemistry, or to say most synthetic chemistry, would involve some sort of rearrangement of atoms or molecules to break and form new bonds. I mean, that's what the joy of synthetic chemistry is. And to kind of build something like this, for example, from ground up, I don't think at the moment there will be a robot that will build that for you. If you think you can just put that into a computer and somehow magically some sort of robot on the side will be able to work out all the possible things, be able to execute it, and then just spew out the compound on the other side. I think we're still a long way from that at the moment, to be honest with you. But the key thing is, while that is kind of a mechanical side of it, might be improving from day to day, and there's been some really wonderful things that's been done, no doubt about it. I think fundamentally the decision as to where, how, what to make is fundamentally a human endeavor, and only a human being can kind of define. For example, here, how productive do you, how efficiency, obviously, in living in the world, we do productivity and efficiency is always something that we want to achieve. Waste management and sustainability becoming top of the agenda as well. With my role at the ACS, green chemistry and engineering, certainly, it is something we becoming more and more, not just making a reaction work, but, ultimately delivering also a sustainable, less wasteful solution. And then on top of that, I might decide as chemist, depending on what I'm trying to do with this molecule, what is the quickest way. If I'm trying to manufacture it, maybe quickest way might, what is the most reliable way? What's the cheapest way? What's the cleanest way? And what is more manufacturable? Now, it'll be in the ideal world, of course, all these things can be the same thing, but in reality, most of the time, you kind of had to make a decision one way or another. And this is to say, this is kind of a whole area of process system engineering, it's a kind of almost a chemical engineering decision when you have multiple decisions that you have to make at the same time. You're trying to optimize everything, right? So ultimately, you have to kind of weigh them out in a different way. And I don't think most chemists are educated in that way to think about it in this, because if you ask me, if you want to ultimately optimize a process for being the greenest or most sustainable, it may not actually end up being the most quickest way, for example. So these are the things that only humans beings, I think, ultimately, or kind of that could make. Now, once we make that decision, then the next question we ask is, okay, now we decided that's what we want to achieve. What can we get our hands on? Is it renewable? What are the potential hazards of what the precursors are, what are their physical properties, so we can design, either to do this in batch or flow, what are the kinetics, what are the heats, signatures, kind of more engineering type question now. And those of you who've been involved in it, you know that thermally heated reactions are kind of almost traditional nowadays. We're also interested a lot in photochemistry, electrochemistry. These are the kind of new tools that's coming online now to kind of understand them, how to use them, what is the best way to deliver your energy and your frontier molecular orbitals. Ultimately, all that decision will culminate in a network of different decisions, and any one of these decisions you make is going to have a knock-on decision, consequence on something else in the whole thing. So really, we had to kind of think about chemistry reactions not just as simply as what's before and after the arrow, but it's also what's above, what's beneath, and what's actually surrounding the entire ecosystem of why we're doing this chemistry. And the problem can become very complex really very quickly. So this is a kind of traditional workflow, I guess. What we do is, we kind of don't need to explain this to this audience, I suppose. You kind of do it in a very traditional way. You design it, you think about it, you record it, analyze, understanding. But really, I'm just going to quickly go forward, and there's many, doing it one factor at a time. I think this will be something that Volker will elaborate on. Very often when you start to optimize a reaction, you change things one at a time. You arrive at the optimal conditions, and then what you do, if you apply the optimal condition, and then you change what's before and after the arrow. I'm sure for those of you who kind of do this, that there's always a question in your mind, right? So you may have like 80% here and then 40% here. Some of you must have wondered, the 40%, if you can go back and re-optimize it, surely, that you could optimize it. But because of the time and energy you need to do, you don't do that. And therefore, because of that, very often, the optimal condition maybe only work for one particular reaction and not the others. And this could lead to a lot of problems with, for example, general absence, the human bias is really the key thing here. So if you can actually rely on data to give us a more unbiased solution, that will obviously be, imagine the kind of things we can start to discover that we may not have even entertained before. Okay, so where we want to be is this, kind of design it in a kind of statistical way with a hypothesis, design not just one or two reactions, changing one at a time, but changing several factors all the time. And when you execute it, execute in a high throughput manner so that you can have as many data points, useful data points, emphasize, as possible, record it in an automated way, analyze and understanding. So you kind of build a virtuous circle around this. And I would say automation is probably where you have on the kind of right-hand side, when you have designed it and then you execute it at high throughput, the robot can really come into useful in gathering of the data. And then analysis, the statistical analysis such as JMP, software and stuff like that will help you understand the data that you collect in a much more meaningful way. And what it could allow us to do ultimately is to have some sort of Google map for chemistry. So let's just say if I want to move here from White City campus to the Royal Society of Chemistry in town, wouldn't it be great if you have a Google map that could plan the different routes for us and actually tell us where the problem routes might be, so we can focus on those areas and not having to think about delivery, the whole thing. This is where we wanted to be. And ultimately, what I want to emphasize is, of course, there are computer-assisted organic synthesis software out there. And, most of you would have heard about the Chemical Cynthia collaboration recently that could kind of do the retrosynthesis for you. But what I want to focus on something is that no matter how good these software and AI algorithm might be, ultimately the quality of the quantity of reaction data is important. And this is where, actually, as a synthetic chemist, this is what our ultimate contribution to the area is, that we have to make sure that the quality of the quantity of the reaction data we collect are good enough for the AI. So there's a very well-known meme in kind of data science, is garbage in, garbage out. So you may have the best model in the world, but if you feed it garbage data, unfortunately, it's going to give you garbage results. So this is something we have to constantly guard against. And the way we guard against it is actually being chemists, thinking about it. Does this result make sense? Does it actually, is it truly innovative, a new observation? Or is it just a way that, our result data is being fed and it's not really good enough, and we have to think about planning using a better set of data. Okay, and this is kind of bring me to this, the whole area of automation and the mechanical side, the right-hand side of things, is where we started to doing, because best will in the world, what if we saying, so for sure, if I want to do a reaction, just one reaction, I can send a student or a postdoc into the lab and do the reaction. If you just want to do that reaction, it's probably quicker for a human to do it. But then if we're saying to say, repeat this reaction 10,000 times with slightly different variation every time, then I think that's when the machine comes in, because one misconception is a machine can knock out reactions, 1,000 reactions just like that. Fundamentally, we still live in a Newtonian world, right? So if a reaction takes 12 hours, it takes 12 hours. There's no way a machine can make it suddenly faster, unless, we're talking about heating it better and stuff like that. But other than that, it doesn't necessarily make a reaction faster. What it can do is that it can work 24/7. It can be more repeatable. You can reproduce your data, hopefully, most of the time, in a much more reliable way. So that's what a machine and a robot is good at. I think fundamentally, is it a better chemist? I don't think it is. Is it more reliable? Yes, for sure. So at Raw, we kind of supply the training. So part of this is about teaching actually chemists. So it's not just about, okay, I know how to do this now, press a button and the machine will repeat it 1,000 times. We also need to kind of transfer what we do at the bench as a chemist with both our hands onto a machine readable format, so the machine can repeat what we do as a chemist over and over again. That should not be overlooked. That is really important. And once the machine execute that workflow, the next thing become, how do you then collect those data? What data to collect? Again, it needs a synthetic chemist to define what to collect and how to collect it. So the knowledge to do that is really, really important. And this is where the training and the expertise really comes in. And in terms of current state of play, I would say we're probably very good in running. You and I all heard about these wonderful 96 wells, 2,148 wells plates. We can allow you to do reactions in parallel very quickly. But what it does is, what we do still collect. Whoops, sorry, that's. Sorry about that. What it fundamentally also only tell you is you only get one data point for each of these. Okay, if you're running a kinetic reaction, you have a temporal data, you collect a lot of data points, but fundamentally it's one reaction. So what's missing is somewhere between the two. Can we actually collect a lot of data from each of these wells? One of the major bottlenecks is how do we actually, analyze, have a fast in situ analytical tool that allow us to look at all 96 wells all at one time, what's happening in each well, simultaneously. I think that is still a lab of the future kind of challenge. So while we say round bottom flask chemistry is down here, one flask, one reaction, synthesis 4.0, as I call it, industry 4.0 is, can we kind of scale that up so we have multiple flasks running multiple reactions at the same time, collecting data at the same time? I think this is where we want to go towards eventually. Okay, let's have a look at what the workflow will look like for a 21st century chemist then. So this is the data, we could have collected it by hand, as in this case, it was actually collected by one of the automated routines here. So as humans, we will start to want to compare, entries, the kind of very classic way of comparing entries 1 to 8. What does that mean? Okay, and then with some assumption, then compare entries 3 to 4, for example. This is a kind of workflow we're familiar to most synthetic chemists. What we really want to do, and hopefully Volker will show you, how to do it, is actually correlate them, correlate not just one factor at a time, but actually multiple factors. Because what a machine or AI or algorithm or statistical science is good at is it can actually find non-linear correlations, not just principal component analysis, but actually how they're correlated, multiple variable analysis and multifactorial dependencies. That's what is very good, because it's good at spotting patterns. And ultimately, it's kind of an unsupervised way is to feed the data to an AI algorithm, and it will actually form a called neural network type correlations, was the second thing. And I really believe this is the way that, in terms of how we think about data, is where we're going towards and where we need to go towards in the 21st century. And learning some of the skills are absolutely critical. So so my next question is, I'll see some of you in education. what do we actually need to teach? And then Imperial College is starting to do that. We're starting to include, some of these topics, incorporate them into our undergraduate curriculum, teach them Python codes in the first year so that they know, how to manipulate. I know data manipulation sounds really bad, but you know what I mean. To what to do with a large amount of data, not actually to manipulate, to clean them up, to visualize them, to analyze them, eventually leading us to modeling, and then before you move on to the robots and machine learning algorithm. So basically, this is me. So this is me working in the 20th century lab in the 1990s and 2000. This is what we do. We kind of work reaction one at a time. But fundamentally, chemists in the future should look a little bit like that, in front of a computer controlling reactions that's happening in a robot somewhere else. So this is what my dream of a future should look like. And some of you might think, where do we have time to squeeze in these things? And I'll argue that, think about the things that you teach in your undergraduate curriculum. Are they all necessary? If you don't have to teach some of the things that ultimately will not be useful, maybe you would have time to teach some of these new things that will be useful in the future. So this is a challenge for us as an educator as well, to think about, what we're delivering to our undergraduate, whether they are relevant anymore for what they'll be facing in the future. And so last but not least, so there's 3 different initiatives. So if you want to know more, obviously, we're doing a lot more. I can't possibly go through everything we've done in the last 3 years. So if you're thinking about running a facility, automated facility such as RAW, please do come and talk to us. If you want to, learn more about it, contact us through the email that's been provided. If you're interested about, educating the next generation of chemists, we have a graduate program here that we're running the last 2 years. We're trying to deliver on some of the aspirations and some of these topics I talked to you about today. So you'll be doing that. So if you're interested in that, come and talk to us about it. And ultimately, if you want to engage with us on the research front, maybe you have some, really interesting project that you think will really benefit from the digital chemistry approach, then come to us. We have a multidisciplinary network of chemists in DigiFab, which will help you hopefully tackle some of this research problem that you might have. And I think that's my last slide. My last slide is really as a joke, just to remind everybody, this is my favorite quote. If we have data, let's have data. If all we have our opinions, let's go with mine, right? And because we're in Britain, I can't help it. This is a consequence of what you might happen if you use bad data. And I think that's it. Ben?
Mimi, thank you very much. I think that's the first time that Boris Johnson has turned up in a Chemistry World webinar. So thank you for that. Yeah, thank you so much for the presentation. Excellent to have you with us. Mimi will be hanging around for the Q&A bit after Volker's presentation. But for actually one quick question, Mimi, you mentioned teaching code and Python, for example, in undergraduate courses. Did that come from the undergraduates who've clearly seen that this is the direction they need to go and they were requesting that, or has that come from further up where you think these are skills that need to be impressed on them?
We are very lucky. We have appointed some excellent teaching fellows and have members of staff who are very passionate about the subject. So they actually encountered their Python code in very first year. They have a build your own spectrometer experiment where they first encountered it. Don't get me wrong, I have QTs, they complain about it quite a lot in their first year about Python. They would have never come across it before. It's very difficult for them to learn it. But I think most of them, by the time they get to the final years, when they get given a lot of data, they really appreciate it. Well, they might not still enjoy doing it. They at least appreciate it. So I think but the important thing is to instill into them in their first year. So for sure, it's kind of it's a little bit, or they don't know what's good for them a little bit. So you do have to kind of carrot and a stick approach for sure. Yeah.
I'm sure they come to understand the value of it. Anyway, we're going to run another poll now to find out a little bit more about our audience. This is another good opportunity for you to type in those questions for Mimi that you may have had while you were sat back absorbing, enjoying the presentation. So let's run the second poll. It's a bit more about your approach to statistically designed experiments. So at the organization you work at, statistically designed experiments are the standard approach to collect data. They're used by some groups or they're not used used. And of course, if you don't know what a statistically designed experiment is, then Volker will have a little bit more background on that, but it would clearly suggest that they're not being used, but we'll let you put that in anyway. And this is all to do with the ways that we actually approach experimentation in the first place, and whether we go down a very traditional sort of one factor at a time route that we're taught at school, where we only change one quantity and then we rerun the experiment and we keep doing that, or whether we use a more designed experiment approach, which is the sort of linchpin of JUMP's approach to doing experiments. So we're going to give you a few more seconds to vote in that, so we get a really good idea of what you're doing out in the audience. But yes, a little reminder that this is a good chance for you to get your questions in. We will have time for Q&A after Volker's presentation. He's doing a software demo for us in just a minute or so. But we will only have about 10 minutes for questions, so get your questions in now to make sure that we have the best possibility of asking them on your behalf. And thank you for the questions that have already come in. That's probably enough time on this poll now, so we'll close that and let's just share it so we can see, and you can see how you fit in with the rest of our audience today. So 28% are using statistically designed experiments as your standard approach for data collection. 38% find that some groups use it but others don't, and 34% are just not using this approach to experimentation. So it's a reasonably even spread throughout all of the answers, and some of you clearly may already use JUMP's software. Some of you, if you're not doing statistically designed experiments, may have not encountered it before, but now is therefore a great time for us to hand over to Volker, who can show you JUMP in action and show you how you can make the best use of it. So Volker Kraft, just a little reminder, senior academic ambassador at JUMP, background in electrical engineering. He used statistical methods to study psychoacoustics and speech communication. He's used that in customer advocacy for people like Vodafone and Voxio, so he's got good industrial experience and he knows the software inside out. Volker, thank you for joining us and thank you for showing us JUMP. We can't hear you right now, Volker. We can see you and we can see your screen, but let's just make sure that your microphone is unmuted as well. There we go. We've got you. Thank you ever so much.
Okay, thanks again, Ben. And many thanks to Mimi for her inspiring and insightful talk today, but also for the fruitful collaboration and still growing collaboration we had with Imperial College London during the past years. On the left of my screen, you see the course about design and analysis of experiments in chemistry and engineering, developed for and also developed and taught with Imperial College and with Mimi's team. So let's have a sneak peek into this course after setting the stage and showing why one factor at a time is not the recommended approach for most studies, as also Mimi pointed out earlier. We have a short recap about ANOVA and also about regression. Before we focus before we also look into classical designs, let me open this from the JUMP starter. So we also touch classical designs, including fractional factorial designs for screening and also response surface designs before we actually look into optimal design using the JUMP custom designer and augment design, both for the highest flexibility you can get today, fitting the design to your problem and not vice versa. And then we also look into definitive screen designs, a more modern approach, and this for the highest efficiency in many cases and many studies today. So here is an example, which is a design table using this definitive screening design platform in JUMP. And what we see here is the design table for this multi-factor experiment. And in this experiment, we are using this design table, which has been designed with 5 continuous factors. So that's pressure to time, our 5 factors. And as you see, we test each factor at a low and a high level, and also at a center point or midpoint. And our response is yield in this case. So I can also select some yield cases here, or yield results, actual measurements we got from the experiment. And of course, yield should be maximized. So JUMP still remembers our goal, what we want, and why we created this design. So we said at the beginning, at the very first step, we want to maximize our response, which is yield in this case. And there are also some limits set here on our response column. And just by selecting some good results, very high yield values, before we actually build any model or run any analysis, we can just look at the data. And if you look at pressure, this seems not really to affect yield. So they are all the same here. If you look at modifier, this is different. So here we see the higher the better approach for this factor modifier. If we look at time, that's a bit tricky, and you will see why after analyzing these data. But before we look into the analysis, I just want to go back, and in JUMP everything is integrated, and with this design table you are ready to start the analysis, but I just want to show you how this was built. So this is the design platform we used, a definitive screening design, and we specified the response. We set our 5 factors with their ranges to test, and then we get a preview for this design. And before you actually run the experiment, you can also look at many diagnostics. For instance, you can check the power. So that's the probability to detect an effect which is really active. And this power looks quite good. You can also look at a prediction variance surface, for instance, to see the variance in your design space. And you can also check aliasing. So that's the correlation between our effects. And of course, we want to have them independent or uncorrelated. And you see here wide is perfect. And we have this wide space here for all our main effects, but we also have the same for the 2-factor interactions with the main effects, and we would see the same for quadratic terms and main effects. So that's perfect news, and that's one of the strengths of this design type. And so this is just one of the design platforms and design types you can get from JUMP. And as I said, it can be a very, very efficient way to learn from your data. So as you see here, we just collected 13 measurements. So we have 13 runs on this design, which is a very small data table for this problem, a very small experiment as well. And another good news is that we also have analysis scripts stored automatically by the design tool. So we are ready to go to analyze our data. And for this, I will run this script here, which will just build a linear model, use a linear model, multiple regression. But I just wanted to point out that JUMP and especially Jump Pro also have many ways to use machine learning. And here we have also a platform for a neural network with several hidden layers and boosting and so on. So these are more the machine learning approaches Mimi also mentioned. Yeah, so we have unsupervised, supervised learning here. And Jump also has a scripting language. Yeah, just let me show you this here. So this scripting language called JSL, Jump Scripting Language, can be used to integrate also with other software. For instance, with Python, which has been mentioned earlier. So this can help you to clean up and to prepare your data in Jump, then connect with Python and run any specific method in Python, get the results back into Jump, and then tell the story about what you've learned in Jump using the interactive visualizations. So here I use one of the analysis tools which were prepared for us by the design tool. So I just need to click the green triangle and I move on to see the model. So this is the result from the modeling step. And as always, you get some diagnostics, and also this one here, which looks pretty good. And then we have this high-level summary here, which is a ranking of our model effects. So these are the most important, most significant effects. Yeah, and we see that we have these three main effects. Please note that pressure is not shown here. So that's where we saw, probably no effect. Yes, no effect by pressure, also no effect by agitation. So they are screened out, and we have these three main effects, but we also have one two-factor interaction, and we have a quadratic term for time. And please note that this is not an indication that there is something going on which is non-linear. No, the definitive screening design directly points us to the time factor, which has some non-linear effect on yield. Yeah, and in Jump you can see a lot, and to see what's happening here in our process, look at the profiler. Yeah, so here we see the two linear effects for modifier and temperature on yield. Yeah, and with our red settings, yeah, so this prediction profiler predicts an average yield of 76%. What's already quite good at these mid values here. And we also see the nonlinear effect of time. This is not just a visual plot, it's also interactive. It's in Jump, so you have everything interactive, and that means that we can explore our factors and change one factor and see how this affects our response, or maybe even responses, but we also see how this changes the relationship with another effect, and that's this interaction here, so we can actually see on the profiler. Now, maybe this is some good news to you if you think you should be robust on temperature. So setting or choosing a high modifier value would get you to a flat relationship with temperature. So this process is pretty robust to any changes on temperature. Yeah, and we also see the quadratic curve here, and here you see why we saw this pattern on the time header, because for mid values and high values we have a quite good yield, but for a short time we really get less yield immediately. Yeah, so that's because of this nonlinear relationship. Yeah, so you can see a lot just from your model by looking at the profiler. And what we also do and cover in the course is looking at a more robust design. And for that, we also use the built-in Monte Carlo simulator, which is another tool built into this profiler. And here I can specify some random variation we may have on a certain factor or on several factors maybe. And then I can simulate yield values. So here we are looking at 10,000 simulated yield values. And with these factor settings, which are still at the mid point, so this would tell us to expect a defect rate of 24%. And let me check the best settings. So if we now simulate again, oh, we are all set. So now we already have a defect rate at 0, just having some random variation on a single factor, which is temperature here. And this is not really a big problem because temperature is flat now, the relationship, and that means that this variation here cannot really populate onto the response. So this is what we do during the course, just looking at one data set and one example. And if you're interested to teach DOE in doctoral training or in master programs, please visit our website, jump.com/doctoral training. And then check out the support and the material you get and we provide on top of a standard academic site license. And here you see that you would get free access to all the course material, including the journal you saw, all the data sets, PowerPoint slides, everything. So you get access to the course material, but you get also train-the-trainer support, so to make you more independent, changing the course, further developing the course, and also teaching the course yourself. But we are also here to help, and we really enjoy co-teaching on site, but also online, what we did a lot during the last 2 years. And here's our special offer today. If you're interested to learn more about this and about teaching DOE in chemistry, just request your DOE starter kit today. And this kit would give you free access to JUMP with some help from us getting you started. And that's all I wanted to share today.
Thank you, Volker. Thank you for joining us. We have a few minutes left for some questions, but just before we're going to go into one last quick poll that's just helpful for us. So we'll launch that quick poll now. We just want to know if you'd like to receive a DOE starter kit from JUMP, just so we get an idea of what sort of proportion of the audience today are actually interested in picking up that starter kit that will help you academically to teach DOE, but maybe help you yourself to learn a bit more as well. So we'll run that poll just shortly. And before we go into Q&A, a little reminder, everybody who's attended this webinar live will receive a certificate. So just keep an eye out in your inbox for a certificate of attendance. That's our little way of saying thank you. Also, we don't share the slides from our webinars because what we think is important is that you get the slides and you get the context of what's being said at the time. And obviously in this case there was that little demo of JUMP as well, which you wouldn't get from a slide deck anyway. But what we do is we make the recording available instead. So in the same email that you get your certificate, you will also get a link to watch the recorded version of this webinar again. So if you just wanted to pick up on anything that you've missed, if there's something you just wanted to dive into a bit deeper, then that recording will be in your inbox in the next few days once we sorted a few things out. So keep an eye out for that. There's also an exit poll on your way out that really helps us to shape our webinars and make sure that we're asking the right sorts of questions, inviting the right sorts of people. Please do spend a couple of minutes just filling that in. We really appreciate it. Thank you. That's probably enough time for this poll. We'll just close that down. You don't need to see the results for that. We'll get Mimi back on screen as well. People were asking in the questions for links. So as we just mentioned, that DOE starter kit, email Volker. His email address is on screen now, and we've just shared it in the chat. So do drop him a line if you want to get your hands on that starter kit. There is also the opportunity to try JUMP free for 30 days. That is at jump.com/try, which is a very easy URL to remember, but we will also share it in the chat if you want to copy it out. Let's now take as many questions as we can fit in. Let's start by sort of tying your two presentations together. Mimi, why did you choose JUMP for your projects in particular when there are other approaches or other ways of doing your statistical analysis and experiment design?
Wow, the answer is kind of quite easy. There are other software packages, of course, but my first engagement with Volker was back in Dow Molecule Grand Challenge. Okay, you remember those halcyon days? So I mean, for sure, I mean, one of those things, you know, is JUMP is one of the people that I've kind of first interacted with. The experience has been very overall positive. When we start looking, when the raw gets started, actually Volker is one of the people I contacted first. He's always been like that, you know, very responsive, very good. And also reviewing the options, we just felt that JUMP, I mean, I'm not saying that that's the only way you can do it, but we prefer to use JUMP because of our overall experience. And I think what they offer is really good for an academic institute. We have to have the ability to work multidisciplinary manner. So a software is not good enough just for the chemists to use it. You know, you want engineers to use it and biologists to use it. So in that kind of way, we also know that other colleagues in other departments are also already using them. So that's, you know, kind of lowers the barrier somewhat. In my experience in the graduate school, graduate program we've been running, I think the software just as a user experience, most of the students seem to be able to take to it quite quickly. I think within a couple of weeks, they're up and doing their own design. But most of all, let's not forget that. I'm not going to reveal how much our academic license is, but let's just say they do a site license. It's very reasonable what we've been offered. It will be silly for us not to take it. And by paying for it, it's quite affordable, let's just say. And all our colleagues over in Imperial College can do that. And that's not actually, surprisingly, not something that you could get with all of the other types of software. Sometimes they just charge per user, which is obviously, you know, there's kind of a little bit inequality in it. And because we have the site license now, if I start talking to a student in engineering, they say, well, we're interested in this DOE, just go and download it from a server. All Imperial College students can have free access to it.
And that helps to encourage I was just saying that helps to encourage the multidisciplinary approach that you were talking to, because it's not siloed off.
Because it's not too, you know, certain software are kind of designed for chemists and they use chemist languages and stuff like that, which is great if you're a chemist, but I think it's not so great if you're trying to work with other people. And in terms of teaching, I mean, for those of you who are interested, this teaching the trainer thing is a really great thing that they're doing. So they're not saying, you know, it's exclusive to us. You can, you know, the only training will only come from Volker or anything. He's actually willing to come and work with our teaching fellows and stuff like that to actually design a course which is relevant to our users. And that shouldn't be overlooked, the importance of, you know, willingness for them to do that. It's really important for us to make sure that we're not just teaching a generic program, but we're teaching something that's relevant, for example, for chemists. Yeah.
Excellent, thank you. We are running low on time, but I'm going to let this overrun by a couple of minutes just to squeeze in a couple of extra questions. Vaishnavi has said, as a chemistry undergrad, how can I get started with statistical analysis? Volker, can we come to you first? Because clearly there's lots of resources available for somebody who is, say, at an undergraduate level to actually make their own start into this.
Yeah, good question, and thank you, Mimi, for your kind words. I just want to react to your previous answer, and it's always a pleasure to working with you. I also have to say to the question, a very good question. Yeah, there's a lot of material out there. Some material which is already accessible for you, and it's also free, is our online course about statistical thinking for industrial problem solving. And you can access that course as well if you Google for statistical thinking JUMP. You can access the course for free. There's a module about designing experiments, which provides all the basic concepts, and that's maybe a perfect scope to get started. But you also get access to JUMP in the cloud, so that means through a browser without installing anything on your local computer, and that gets you started immediately, and you can play with the software and look at the examples and also the hands-on instructions, and you get also a nice introduction there.
Thank you. I think we'll have one more question, and this one is it's not software specific, it's not even academic genre specific. This is one of those great general questions. Mimi, you mentioned the general garbage in, garbage out principle, that no matter how good our analysis, if our initial data is garbage, then what we get out of the end is useless. And Emanuela asked, how do we find out? Or at what point do we find out that the data that we've got is actually garbage? Volker, I think you, from a software perspective, can probably help with this answer as well. But Mimi, from an experimental perspective, at what point do we know this data isn't going to help us?
Yeah, for sure. Yeah, understanding what those p-values and RMSE values, these are again the kind of more technical things that could help you make that decision. But I think Volker, during Volker's talk, I thought for example, he showed the selection where you determine temperature, reaction temperature, stirring rate, and stuff like that. Who make those decisions? Chemists. We decide what factors we want to look at. A machine is not, that's what I mean. You still need that input by chemists. And I also encourage at the end of it, part of difficulty actually teaching this course is for the students to so for example, Volker, you have this thing about the p-value has to be less than 5% for it to be significant or something like that, right? But, understanding this figure is one thing, but then be able to connect it back to the chemistry itself and you go, does that make sense? So one of the things that we like to tease our students is before they start the design of experiment, I say, I predict reaction temperature and reaction time going to have a strong effect. This is and then they do the experiment, they go, oh, the longer you leave the reaction and the higher the heat, the temperature, the yield is better. Ooh, cancer free, right? I mean, so there are things that you expect, but I think what's exciting is it can actually show you correlations not so obvious, as we said. And a lot of that is to do with practice. So it reinforces you, it challenges you to become a better chemist, a more thoughtful chemist. I think that's why I feel very enjoyable about that. It's not just all the sexy or, I have more data to tell me, but actually you can probably see into things that you probably wouldn't have expected other than just temperature and reaction time, other things that you would not have naturally have expected from it. And that's ultimately how you judge whether the data is good or not, whether it's telling you something that is good or not. And then of course, then you design the next set of experiment to test that hypothesis, right? Sure, Volker will not disagree with me.
So yeah, Volker, how do we've got a data set. What can we do to say, is this actually valid data? Is it worth using?
I think that there are maybe two answers from my side. One is look at the data first. You can already see a lot probably before you run any analysis. The second answer is yes, JUMP is a statistical package. So there's a lot about statistical significance and p-values and so on. But there are also other tools built into JUMP which are more about practical importance of your effects. And that could be also maybe an interesting topic to look for and to look into these tools, which are maybe more relevant than p-values.
I see. Well, I think we are out of time. We have overrun. So thank you to everybody for sticking around with us. Thank you to Emanuela for that question. Really nice way to bring this to a close, I think. So we've just also shared in the chat, we shared Mimi's email, we shared a link to Imperial Raw, we shared a link to the STIPS course. Grab those, click them through to open them in your browser and the Jump free trial before the webinar ends, or copy and paste them for use later. Or they have been on screen, so just come back and watch the video if you wanted to follow up on any of those links. We will send you an email very shortly with the certificate of attendance with that recording, and that's just our way of saying thank you for attending live. It really helps these events when we have good questions, a good engaged audience like yourselves today. So thank you so much. You could have just watched the video in your own time, but being here live with us really makes the difference. And that's really what makes the Chemistry World webinar experience a positive one for all of us. So thank you to you all for joining us. Obviously, a huge thank you to Mimi Hii and to Volker Kraft for joining us today, and thanks to Jump for helping us to put together a series of webinars and events, always finding ways for chemists in academia and industry to improve their research, improve their handling of data, and get more out of that data. So we're really pleased to work with them. They're one of our valued partners here at Chemistry World. So keep an eye out for that inbox. We will send you everything you need to know. And if you have a look at chemistryworld.com/webinars, you'll see all of our upcoming events that are able to be registered for now. So have a look at that as well. And we hope to see you in a future Chemistry World webinar. I'm Ben Valsler, Chemistry World's digital editor, and I hope we'll see you again soon. Thanks again.